So let's talk about Virtual Extensible Local Area Network, or Vxlan. This is just the basic discussion of Vxlan. Why? Because Vxlan can be really complicated. For those who are new to this channel, welcome. I am your host, name is Dean Armada, and I'm the Cloud and Data Center! Rock Talk! And on this channel, we talk about tech careers and certifications, trivia tutorials in cybersecurity, trivia tutorials in cloud and data center, and my journey as an IT instructor. So feel free to check out the rest of the channel and consider subscribing. The reason why Vxlan or Virtual Extensible LAN is very important is because it solves many data center environmental issues. And maybe you're thinking, these are not the only data center environmental issues. We have security, we have routing, etc. Yes, there are issues, but not specific to data center because it can happen in many other network environments. But VLAN limitations, scalable data center design, which is the spine and leaf topology, and layer 2 extension in between layer 3 boundaries is one of the most common data center environmental issues. And we are going to talk about Vxlan and how to fix all of these three issues. Now, first, we're going to do a little warm up, okay, like a refresher. And what I'm going to do next is I'm going to create a very basic topology. We have switch 1 and we have switch 2. Okay, we have switch 2. And under switch 1 and 2, I will connect a pair of PC. Okay, so this is PCA. And a pair of servers as well. So this is server C. And I will also add the VLANs. So both PCA and server C are assigned in VLAN 10. I will also connect another pair of PC and a server. So this is PCC and this is server D. There you go. And both are in VLAN, not 10, but 20. Right there, VLAN 20. So assuming these switches are layer 2 devices, we agree that PCA and PCB cannot communicate with each other. Why? Because they are in two different VLANs. Now, how about PCA and server C? Can they reach each other? Think about it. Or PCB and server D. Can they reach each other? They are in the same VLANs. VLAN 10 for PCA and server C, and VLAN 20 for PCB and server D. If you think about it, Can they? No. Why? Because switch 1 and switch 2 are not connected to each other. Now, what we can do is this. I'm going to connect a dedicated link between switch 1 and switch 2. This is VLAN 10. And a dedicated link between switch 1 and switch 2, which is VLAN 20. Okay? We can do this, right? PCA to PCC and PCB to server D. But this is a bit stupid. Why? Because we are creating the number of links per the number of VLANs configured in our network. Okay, and if we have 10, 11, or 20 VLANs, that means we will be wasting 10, 11, or 20 ports per switches. So the best strategy, the best solution for this is just connect switches, both switches, to one physical, or it can be also logical connection, okay, or logical link. And this is what we called trunk port or trunk link. On other vendors, they don't call it trunk, they call it tag interface. But regardless, they're using the same protocols anyway, which is 802.1q. Okay, and let's have a little review about this protocol. So it can carry multiple VLANs. Well, by default, it can carry VLANs 1 to 4094. I don't want to say it can carry all VLANs because take note, some VLANs are reserved. So what happened here really is it creates a new field in our Ethernet header. So let's assume this is source and destination MAC address. It adds a new field, which is tag field. Okay, and this is in between the source and destination MAC address and the payload. Okay, so this is the payload. And inside the tag field, we have multiple values, but the most important is the priority and the VLAN ID. Okay, now the VLAN ID, this is 12-bit. I'm gonna add here 12-bit. Oops. And this 12-bit is equivalent to 4,000 plus VLANs. Okay, so 4K plus VLANs. And how it works is this: when the PCA sends traffic down to switch 2, the switch 2 will receive it. Since this interface is a trunk interface, it will look for the tag value. Again, the priority, which is the COS, and the VLAN ID. Now, since this traffic is from PCA, that is the source, it would see, hey, you are VLAN 10. And I can forward this only to those interface that is a member of VLAN 10, such as the interface connected to server C. Okay, so that is just a refresher, 12-bit for the VLAN ID, which can accommodate 4,000 plus logical segments, which is VLANs. Okay, so these are VLANs. Now, let's talk about Vxlan. Okay, so what I'm going to do is I'm going to create the Vxlan header, and here's how it works. So on this part, I'm gonna add payload here. Let's do it again. There, so this is the payload, and we have the tag here, and source and destination. Again. So what you see here is this Ethernet frame. Okay, we just move it to the Vxlan header. Now, which is important? The very important part is this new field. We call it Vxlan ID. Okay, and the Vxlan ID, it is used to encapsulate our Ethernet frame using the UDP 4789. Okay, so this is encapsulated. So let me move here. Encapsulated. UDP 4789. And what I would also like to highlight is on the outer header. So this is the outer header. Okay, I'm gonna add source and destination. This are MAC address value, and another source destination. These are the IP address value. Okay, so these are all routable. Okay, routable. And take note, we have the Vxlan ID, and let me redo this. So this Vxlan ID here, this is not just 12-bit. Okay, 12-bit is for the VLANs up to 4,000 plus logical segment. This is 24-bit. When I say 24-bit, it's not just twice the 4,000, because twice the 4,000 is 13-bit. 24-bit means up to 16 million plus logical segments, and that's how many logical segments a Vxlan traffic can use. And this is the reason why the Vxlan can solve the first data center environmental issues. We have VLAN limitations. Okay, now in a very large data center environment, 4,000 is not enough, which is rarely happen in an enterprise network. Okay, so let's continue using the next diagram. So what we have here is server 1 with an IP address of 192.168.10.1, and this is behind R1 or router 1. We also have router 2. Behind router 2 is a server with an IP address of 192.168.20.2. Now, what's this for? Well, we want to compare VXLAN to a very common tunneling mechanism or tunneling technique. Can you guess what it is? You're correct. This is generic routing encapsulation or GRE. And how it works is this. We have two endpoints, router 1 and router 2. Our goal is for router 1 and router 2 to communicate to each other as if they are directly connected to each other. And the reason why we want to do this is we want to route these two networks, okay? It's like they are just one or few hops away to each other. Now, how it works is very simple. Well, first, we're going to add an interface loopback. So I'm going to add an interface loopback, let's say loopback 0, okay, with an IP address of 1.1.1.1. We're also going to add a loopback IP address on router 2, 2.2.2.2, okay? Now, in GRE, we create interface tunnel 1 or 0, it doesn't matter. And then we supply the source, which is in this case loopback 0. And the destination will be 2.2.2.2. Now, under router 2, we're going to do the mirror configuration. Interface tunnel 1, the source will be loopback 0, which is 2.2.2, and the destination is 1.1.1.1. Now, what's going to happen is this, okay? Assuming everything is other configuration required are working. Let's say router 1 and router 2 can communicate via loopback 0. They will be able to create a tunnel. Take note, router 1 and router 2 is the one who encapsulate and decapsulate the traffic. We do that via the interface tunnel. Now, what will happen here is the router 1 and router 2, they will be able to communicate as if they are connected to each other. Of course, we need to add a tunnel IP address as well. We'll just skip this. But once they are, let's say, configured properly, all complete, this server with an IP address of 192.168.10.1 will be able to communicate via tunnel, okay, to the second server, 192.168.20.2. Of course, we also need to add routing. It can be static or dynamic routing. Okay, so that is GRE. Very simple. We created a tunnel in between layer 3 devices. This can be the internet, okay, and we can have multiple layer 3 devices, routers or service provider routers, etc. Now, what I'm gonna do is I am gonna copy this topology, but this time it's more of a comparison purposes because we want to compare GRE to VXLAN. Okay, so we're gonna copy, and I am going to erase some parts. All right, so I'm gonna erase some parts. We don't need to discuss all of the details. All right, and then there you go. Now, we're going to have the same topology, but we're going to modify it in a bit. What I will change are the endpoints. So we don't really need a router. Why? Because in VXLAN, most of the time we use switches. Now, I believe some routers already have VXLAN capabilities, but VXLAN started with Nexus devices, Nexus switches. So I'm going to convert this to Nexus devices, and the Nexus devices, we call this VTEP. Okay, it stands for VXLAN tunneling endpoint. Like what I mentioned, the endpoints are not routers but the switches. So I'm gonna rename this VTEP1, and this is VTEP2. Now, another modification that we're gonna do is this IP address. Okay, VXLAN allows us to extend layer 2 from one location to another. So it can be in two, or not two, but in the same network, same VLAN, although in two different or more locations. All right, so this is the setup, okay? Now, In VXLAN, we don't use interface tunnel configuration. We use interface NVE1 because this is Cisco Nexus devices. And it's almost the same concept. We do the encapsulation and decapsulation. But the goal here is almost the same. We're able to extend the traffic from one location to another, but this time in the same network, in the same VLAN. Okay, and this is in between layer 3 boundaries. So let's say this is MPLS cloud, and we know there's a lot of routers in the MPLS cloud. And like what I mentioned, these are all VXLAN. So this is the VXLAN tunnel. Okay, like what I mentioned, these two servers are in the same VLAN, in the same network, but they can communicate to each other in between or in two different locations, let's say two different data centers, but in between multiple layer 3 devices. So that is another use case of VXLAN. So this is the third layer 2 extension in between layer 3 boundaries. Now the next use case of VXLAN is for scalable data center design. Now I'm going to draw our topology, and what I'm going to do is I will add, this is spine 1, this is spine 2, and I will also add 3 leaf switches. Okay, and each leaves are connected to servers. Now the servers, I will add their IP addresses: 192.168.10.1, 192.168, 10.2, and 192.168.10.3. There you go. So as you can see, 3 different servers in the same network. Okay, 10.0/24, let's assume. Now here's the question. This is leaf 1, right? Leaf 1, leaf 2, leaf 3. Now here's the question. In a spine leaf topology, and when I say spine and leaf, we can scale this. We can add more spines, we can add more leaves. It doesn't matter, because again, this is the goal of this topology. It's scalable. Now here's the question. In between spine and leaf, what is, or which protocol shall we use? Is it layer 2 or layer 3? Think about it. If we use layer 2, this may cause loops, right? Especially if we connect leaf 1 and leaf 2, or the switches, or leaf switches, excuse me. And that's what we want to avoid in a data center environment, because in data center, we don't block ports, okay? As much as possible, we don't block ports. We make sure that all of the interface are utilized. So we're gonna avoid layer 2 interfaces. Okay, layer 2 interface in between spines and leaf is not something that we recommend. So in short, we'll be using layer 3. But is it not complicated? Because if we use layer 3, we'll be configuring every single interface in between spine and leaves. Yeah, I know it can be very cumbersome, especially if we have many spines, many leaves. Okay, but we'll talk about that in the later videos. Now we want to discuss the concept of VXLAN in a spine and leaf environment. Now, layer 3, right? So we're going to configure this interface, this interface, this interface, this interface, and so forth. Now the question is, if we configure IP address on those interfaces, is the routing a little complicated? Yeah, that's why we need to enable layer 3 or dynamic layer 3 routing. Okay, and we will do this. All of these are routable networks or routed networks. Let's do that again. There you go. So these are dynamic routing. Now, when I say dynamic routing, this can be OSPF, this can be IS to IS, BGP, etc. It doesn't matter, as long as these leaf switches can reach each other. And what I'm gonna do is I will add their router ID / loopback as well. So 1.1.1, 3.3.3, and 2.2.2. So assuming that all loopback, leaf 1, leaf 2, leaf 3 can communicate with each other, we can now move to VXLAN. Okay, so in VXLAN, like what I mentioned, the endpoint is always the leaf. Well, at least in this design, in this topology. Okay, so this will be the VTEP, VXLAN endpoint 1, and VXLAN tunneling endpoint 2, VTEP 3, and VTEP 2 and VTEP 3. There you go. There you go. So they are now the VTEPs. Okay, they're the one who do the encapsulation, decapsulation. We're gonna talk about it in a bit. What I will also add here is the VLAN and VXLAN mapping. And before that, let's look and analyze the topology, our diagram. As you can see, we have layer 3. This is all layer 3, right? But we have our servers in the same network, same VLAN. Let's assume they're all in the same VLAN. How can they communicate with each other if they're in the same network and they are behind layer 3 device? It's not possible. Well, in the traditional network environment, yes. Okay, but this is what? This is data center or advanced data center networking. So here's what we're gonna do. First, we're going to assign the VXLAN ID. Okay, so the VXLAN ID, in this case, we want the servers to communicate to each other. That's why it needs to have the same VXLAN ID. And I'm gonna assign a value of VX010. Okay, I'm also going to assign a VLAN ID. Okay, this is VLAN 10, VLAN 10 on all servers. Now, here's how it works. Okay, at least in this very basic, very simple design. Let's assume that server 1 wants to communicate to server 2, 192.168.10.1 to 10.2. And here's how it's gonna happen. First, it will send to the switch, layer 2. This part is layer 2. It will send it to the upstream switch, and the VTEP 1 or the switch 1, leaf switch 1, will try to discover the destination, 192.168.10.2. It will announce, and it will try to look to the destination locally. If it found the destination, we're done. We're not doing VXLAN anymore. But if it hasn't found the destination, it will try to extend it to other VXLAN members. And how it will work is, since these are VTEPs, and it really depends what type of VXLAN. There's a unicast, there's multicast VXLAN. We're gonna skip to that discussion. But really what it will do is, it will try to encapsulate. So it will do this process. It will encapsulate, since it is the VTEP, it will encapsulate, okay, adding the VXLAN ID, which is 5010, and then it will encapsulate all layer 2 information, the source, destination, the tag, the payload, etc. And it will try to look for other VXLAN members. Of course, they must have the same VXLAN value, 5010. So let's say it's trying to look for the destination by VTEP3. The VTEP3 will decapsulate, and then it will try to forward to the destination 192.168.10.2. But 10.2 is not here. So VTEP2 will do the same. It will decapsulate, and when I say decapsulate, it will strip UDP 4789 and will look for the inner value. And it will look for the tag, VLAN 10, okay, and then it will try to broadcast who owns 192.168.10.2. Since 10.2 is connected behind VTEP2, okay, it will now reach the destination. This time, the server 2, since it is the destination by VXLAN, it will now send a reply directly to the source, which is 192.168.10.1. Okay, and this is where it forms the VXLAN. Okay, so this is the concept of VXLAN in a spine leaf environment. Okay, and of course, this is the VXLAN basic. We're using layer 2 VXLAN breaching. We can also enable a more advanced VXLAN, such as VXLAN layer 2 EVPN and layer 3 EVPN. So we can route VXLAN into one or different VXLAN ID. or group. Now, also, I would like to highlight this. Since Vxlan would look like they are directly connected to each other, I mean the VTEPs, and if we do show MAC address in the VTEP devices, it will discover, or it will appear the MAC address of the discovered destination. In this case, the MAC address of 192.168.10.2. Okay, and this is via or learn via interface NVE1. This is the same case. If we do show MAC address on VTEP2, you will see the MAC address of the first server 192.168.10.1, and it's learned also via interface NVE1. So that is Vxlan. Before, in Cisco Nexus 7K, we have OTV and Fabric Path. Actually, Fabric Path is also available in Cisco Nexus 5000. Cisco stopped promoting those technologies. Why? Because we have a better option, and that is Vxlan.